Hello, and welcome to the session, Science Powering Supply Chain Analysis. In the previous roundtable, you heard from public and private sector experts that are working to improve the supply chain for forest-based commodities. Improving supply chains involving natural resources, whether based on forests or other materials, often involves measuring those natural resources and, crucially, how those resources are changing. So in this session, we're going to hear from three scientists who are pushing the boundaries of how we can estimate the properties of specific natural resources and monitor them over time using remote sensing from satellites. In terms of format, we're going to have a series of short recorded presentations followed by a live Q&A session featuring the three speakers. If you're listening to this live, feel free to use the chat feature to pose questions for the speakers about what you hear, and those speakers will have an opportunity to answer during the live Q&A period. So let's get started. Our first speaker is Zoltan Szantoi, a land application scientist working within the European Space Agency. Dr. Szantoi has worked within the Copernicus Global Land Monitoring Service, co-leading the hotspot monitoring activity. He's a member of CEOS, or Committee on Earth Observation Satellites, where he co-chairs the Land Surface Imaging Virtual Constellation Group. He also serves as a research fellow at Stellenbosch University, South Africa, and he's an editorial board member for the European Journal of Remote Sensing and has co-authored over 50 peer-reviewed scientific articles. Dr. Szantoi will be presenting on mapping oil palm plantation at global scales. Oil palm is a very productive crop used in many packaged products, and it's replacing tropical forests in many regions throughout the world. So over to you, Zolti.
Hello everyone, this is Zoltan Szantoi, and I will be introducing one of our global mapping efforts where we discriminated oil palm plantations using free and open satellite data and state-of-the-art artificial intelligence techniques. First of all, the actual work we are presenting here was published recently in Earth System Science Data, where you can find a very detailed description on what and how we did, as well as the data, which is hosted in several places, among others, in the Earth Engine data catalog under the name Global Map of Oil Palm Plantations. Few words about the topic before we look into the work itself. Oil palm is originally from Western Africa, but extensively cultivated all over the tropical regions. Unfortunately, its plantations took a toll on biodiversity globally in the tropical areas. Beside the well-known issues on biodiversity, here I just added one example of how plantations affect primate ranges in Africa, published back in 2018 in PNAS. Its environmental impacts are also looked at on a broader scale. In another example in a recent Nature Plant paper mentions other negative effects such as on water quality, greenhouse gas emissions, smoke and haze, and social problems such as land grabbing and conflict, labor exploitation, social inequality, and decline in village-level well-being. On the other hand, they also mentioned perceived positive effects, such as it brings economic development to regions with few alternative options, and it generates substantial livelihood improvements when smallholder farmers adopt oil palm, as it produces more vegetable oil than other oil crops per square kilometer, and generally provides higher income compared to other crops. You can also see from the figures that its estimated growing area is continuously increasing, thus having a very accurate baseline map, as well as a procedure to monitor plantation expansions is of utmost importance for the reasons I just mentioned earlier. So we aim to map industrial and smallholder plantations. Both plantation types have the same vegetation cover, oil palm, but the difference is in the spatial settings, like the presence of harvesting roads and other crops, and the heterogeneity of the plantation age. Our product focuses on closed canopy plantations. As you can see, industrial plantations are very alike worldwide, while similar road networks when the terrain is flat, while smallholder plantations can be quite diverse. So now, let's see how different sensors capture closed canopy plantations. Our first step in the workflow was gathering Sentinel-1 and Sentinel-2 images from Earth Engine and generating annual composites. Here, we see them for the year 2019 in two regions, Indonesia and Cote d'Ivoire. These composites show industrial oil palm plantations surrounded by smallholders. Despite being two different regions of the world, both industrial plantations show the same rectangular harvesting road networks. More importantly, a feature that makes oil palm recognizable from such imagery is the backscatter of the C-band radar. Here, the Sentinel-1 composite doesn't show the original backscatter values. They were scaled and oil palm appears green, while the other vegetation in purple. For Sentinel-2, we selected the red band for the classification model, as it has high contrasting values between roads and other features, and thus it helps with the depiction of road networks in industrial plantations. Now about the training and validation data collection. There are plenty of labeling tools, but we considered that Earth Engine was a great choice for collecting such data for two reasons. One, the collection of training data requires the visual interpretation of satellite imagery, and Earth Engine is a convenient tool that can display both Sentinel and very high resolution data, helping the quick interpretation of the plantations. And secondly, the geometries that are delimited using the geometry editing tool in Earth Engine are georeferenced. As you can see on the right-hand side, this plantation was labeled easily based on such underlying data. To continue from the previous slide, we labeled polygons instead of points because we used a semantic segmentation model. For training such models, pairs of X and Y images with fixed size are required. Here, X's are the Sentinel data, while Y's are the labeled images. These training chips of X's and Y's with a size that we set to 1000 by 1000 pixels were selected and labeled in 84 palm oil producing regions. Now, by referring to palm oil producing regions, another concurrent step was the where to map question. While we are talking about a global map and cloud processing, we still want to be efficient. So we extracted the range of climate values in oil palm growing regions and modeled the potential distribution of the plant using bioclimatic variables such as rainfall and temperature aggregates. Once the potential oil palm distribution was estimated, we generated a 100 by 100 kilometer grid that covers the region. Then within each grid cell, we did a 1000 by 1000 pixel subdivision with Sentinel-1 and Sentinel-2 composites. The 1000 by 1000 pixel chips were used because, as mentioned before, the semantic segmentation model was trained with an image chips of 1000 by 1000 pixels. This is a very important in semantic segmentation. It's a very important step as traditional machine learning uses tabular data where values in each pixel are considered separately in the classification model. But in deep learning, CNN in our case, the model doesn't only take into account the spectral and backscatter values from the images, but also exploits the spatial patterns within them. Closed canopy plantation shows the same spectral and backscatter values regardless of whether the plantation is industrial or smallholder. However, the just mentioned spatial patterns such as harvesting roads in industrial plantations make it possible for the model to the discrimination between typology classes. Here we show the previous Sentinel-2 composites in Côte d'Ivoire and the classification image that results from our convolutional neural network model. Red are industrial and magenta are smallholder plantations. The 1000 by 1000 pixel Sentinel-1 and Sentinel-2 composites were classified separately and the resulting classification were merged into one final layer. On the right-hand side, we show the density of industrial and smallholder plantations in the producing regions. So this is one of our output, basically. To our knowledge, the oil palm layer is the first global mapping product based on deep learning model. This is why the ESSD paper, we emphasize the comparison of our results with two similar data sets that employed a random forest model. Here on the right-hand side, we show one comparison where the CNN-based layer outperformed the random forest-based one in detecting smallholder plantations, arguably because it was able to capture the spatial patterns in the satellite images. The accuracy assessment was done globally and provides relatively high accuracy numbers, but here it is important to mention a limitation of our product as the distinctive Sentinel-1 backscatter appears only in the closed canopy plantations. The model struggled to detect young or open canopy oil palm. For this reason, the accuracy could be lower in specific regions where oil palm is grown in heterogeneous settings. Few words about our quantitative finding based on the model output. We found oil palm in 47 countries, but the bulk of the growing area, about 90%, is located in Southeast Asia. There is also quite a difference in terms of smallholder and industrial plantation distributions, as industrials are in the leading plantation types globally. However, West Africa holds strong with the smallholders. Here I would like to come back to the points in the previous slide, as for instance, oil palm is cultivated as a semi-wild crop in West Africa. We can also call it as a feral oil palm plantations. And the canopies don't reach full coverage in this region. This also explains the lower area estimates in some West African countries compared to the official FAO statistics. Most of the steps in the workflow were conducted in Earth Engine. These steps include the modeling of the oil palm distribution, collection of training and validation data, and the generation of Sentinel-1 and Sentinel-2 composites. However, the composites were exported and classified in a CNN model that was trained locally in MATLAB. However, but the entire workflow can be fully implemented within Google's platforms. So one alternative that we explored involves the conversion of the CNN model into a standard format such as ONNX. And this allows the possibility to use the CNN model in other frameworks like TensorFlow. So in this alternative workflow, we could use the Python Earth Engine API to generate the Sentinel composites, which could be classified with the CNN afterwards in Google Colaboratory or using a local computer. We also added other options here, but I will not go into details now. Apart of the technical workflow, so what we can do with such a data layer in terms of broadening science. So for example, if you recall, I showed a Nature Plant paper early on where the authors identified 321 species having oil palm plantations as one of the reported threats. But in the study, they also recognized that the number is probably an underestimation and that there is no global spatial analysis comparing oil palm plantations and species distributions. To fill this gap, researchers will use global data on the distribution of mammal, bird, and amphibian species produced by the Digital Observatory for Protected Areas based on IUCN data and the global map of oil palm plantations. Their study will provide spatially explicit, quantitative, and global estimates of species exposure to oil palm plantations. The exercise will be run for protected areas, countries, and ecoregions to reveal their exposure to such plantations. Here I would like to mention that ultimately we need global maps for all major oil crops so that we can make meaningful assessments of the relative environmental impacts of various crops given their different yield and land needs. We are currently doing this for coconut, another widely grown tropical palm, and we'll soon start with other vegetable oils as well. And since our session here at the Geo for Good is about science powering supply chain analysis, I thought to showcase another ongoing study where researchers are trying to assess the impact of oil palm plantations also on biodiversity, but from a different angle through a life cycle assessment tool. Here, researchers are developing country-specific inventory models considering several aspects such as the land use change associated to 1 hectare of plantation, the CO2 emissions caused by such land use change, and emissions caused by cultivation of drained peatland. Other types of emissions and resources used will be taken from existing LCA databases to complete the models. They will be combined with the global map of oil palm plantations and with a number of impact assessment methods used to derive impact on biodiversity, to understand what are the main drivers of biodiversity loss according to the different methods, for example, climate change, land use change, and how the results are affected by the level of regionalization of the impact assessment method. This project was funded by the European Commission BioPalma program, so we thank the BioPalma program, and we thank you to spend your time to look at this presentation, and I close here, and if you have any question, please let me know. Thank you very much.
Thanks, Zolti. Our next speaker is David Lobell. Dr. Lobell is a professor at Stanford University in the Department of Earth System Science. He's also the Gloria and Richard Kushel Director of the Center on Food Security and the Environment. He's also a senior fellow at the Stanford Woods Institute for the Environment and a senior fellow at the Freeman Sproglie Institute for International Studies and the Stanford Institute for Economic Policy and Research. Dr. Lobell's research focuses on agriculture and food security, specifically on generating unique data sets to study rural areas throughout the world. His work has been recognized with a MacArthur Fellowship, a McElwain Medal from the American Geophysical Union. He's also the lead author for the Foods chapter in the Summary for Policymakers in the recent International Panel on Climate Change, or IPCC, Fifth Assessment Report. Dr. Lobell will be presenting on how to derive agricultural information using remote sensing. So over to you, David.
Hi, and thanks for the invitation to present in this session. I'm going to be talking about how we use Google Earth Engine as a way to improve data on agricultural systems that can inform an understanding of the supply chains. So I'll go through a few things today. One is I'll just briefly talk about broad motivations for what we're doing. And I'll spend most of the time talking about how we actually use Earth Engine to do various things around crop types, yields, and agricultural practices. And then I will take a couple minutes at the end just to give one example of an application where we're looking at evaluating so-called sustainable practices with the example of no-till agriculture. So briefly, when we're looking at field scale mapping of agricultural outcomes and practices, as shown in this example of yield mapping in the Midwest on the bottom, there's a few motivations. One is simply that there's a lot of differences in how different farmers manage their land and the types of conditions that they face in terms of soils and weathers and other factors. And it just provides us a lot of information that we can use in a statistical way to understand the effects of different practices. Related to that, we can also begin to understand in any system around the world, how do you identify the opportunities for raising productivity even higher, which is a really important issue in terms of increasing the efficiency of agriculture in terms of land, in terms of water use, in terms of greenhouse gas emissions, et cetera. And then in particular, this type of monitoring can be really useful as we think towards implementing markets to actually incentivize farmers to do more than just produce food, but to actually provide the ecosystem services that different supply chains may value. So when we are doing this, our basic pipeline, which we implement in Earth Engine, looks something like this, where we are fairly agnostic, but we use a lot of different image sources of imagery, including public satellites like the US Landsat system, the European Sentinel systems, as well as private sector data, increasingly from Planet and other companies. And all of that is providing snapshots over time of agricultural systems, and we do typically some sort of model fitting or compositing to try to summarize the behavior of that system throughout the season. And then we're typically taking the parameters of those models and then using those as information to predict various things related to the crop types, related to the cropping practices, and related to the cropping productivity or the estimation of yield. When we're doing that latter step, we're not only using the imagery, but we typically also incorporate other types of data, whether it's weather data, field data, often we use simulation data, and all of that can be incorporated in some form on the Earth Engine platform by us being able to import different data sets. So before getting into the details, let me just highlight, I think, some of the really compelling value that Earth Engine provides. In particular, it's hard to overstate the importance of being able to access all sorts of different types of data. The team is really good at listening to the community about what would be useful and also keeping these up to date. The time series modeling, as I already mentioned, is a really key component of agricultural monitoring, which there's a lot of functionality. And then finally, we're doing these at the continental scale. And so the ability to process in parallel and be able to map entire continents on the orders of hours is really unique. So I was asked to not spare any details. And so I'll just give you a little bit of flavor of each of these steps. in terms of the time series modeling, we use a few approaches, but a really common one is to look at harmonic regression. So this is basically fitting sums of sines and cosines to different data sets to try to get a good summary of how things are evolving, in particular how in this case, the greenness of the crop is evolving over the season. And these types of model fitting, the Earth Engine community has provided various examples. George Azari has put together a great library of different functions that, for example, will define the sines and cosines as a function of whatever parameters you want to define, and then in terms of how many different sines and cosines, what's their periodicity, and then a whole series of functions to then map that onto different collections. And in this case, I'm showing you an example where we're doing this generically, but we often apply this to Landsat data. So for example, with Landsat in the US, for the agricultural systems in the US, this is showing you for every pixel judged by the cropland data layer to have a crop in this region for that particular season, 2016. This is showing you a summary of how the different how the different regions compare phenologically. So different phases, amplitudes, and overall intercepts of greenness. You can see very clearly these patterns emerging at the broad scale and as well as the fine scale, which is not really shown here. Now we then take those and we will again fit the models, take the parameters, and then start feeding those parameters into models that predict things like crop type. So we've done this with looking at, for example, in the US, corn and soybean areas. This is useful because although cropland data layer from the USDA does exist, it doesn't go back in all the states that we need it far enough. And even where it does go back, it's often noisy. So we've produced these more seamless estimates over time throughout the whole region. On the left is showing CDL from an area in 2001 versus our estimates. In terms of yield, what we found really useful is to take these harmonic curves and then look in particular at the period around the peak and particularly the 30 days after the peak. And that's what's shown here is we're taking here the basically fitting a daily model to these with these harmonic curves. We predict the daily values, and then we're taking a sum over the 30 days post the peak, and that is a key variable that we then use to predict yields. And this is something that Jill Dinas, a postdoc in my group, has been leading. And yes, this shows how we then take those terms here in terms of the different GCVI sums, and then we are applying different mass. But here is the key thing where we're then multiplying it by different coefficients. And these coefficients that relate greenness and weather to final yields are where the simulations come in. We don't use ground data to calibrate this so that we can very nimbly move to different places or different years. We instead use simulations that are being run offline, but then the coefficients are incorporated into Earth Engine. This is an example of what then is produced through this process. This just shows you estimates of corn yields. In this case, we've also done this for other crops as well. And it shows you now at the field level, you can start to get details, or even at the subfield level, of what the productivity of the field is. And this is useful for various applications. We've done a lot of evaluation of this at the field level, again, using Earth Engine to incorporate various field data sets. One recent one is a collaboration with Corteva, which has a lot of field data from their farmers. And we've looked both at direct comparisons on about 1 million fields, but also looking at whether the satellite data are picking up the right relationships with different management variables. So what's shown here is, for example, the seeding rates and the field management data, the planting dates, the harvest dates, and then some characteristics of the environment related to soils and weather. And all of these show that the satellite data through this process are really able to capture these key relationships. And now, as an example of an application, and this is again just one of many, we've been looking at various quote unquote sustainable practices, some of which may well be very attractive from a sustainability standpoint, some of which may be viewed as greenwashing and not particularly useful. We don't know in many cases because the evidence base right now is based on very little, often, some experiments that have been done in some locations. these types of data sets really provide a step change in our ability to evaluate. And one practice that has been gaining steam throughout the last few decades in the US is no-till cropping. And so this is a map shown here. Again, George Azari produced this, showing where we estimate no-till cropping to have become prevalent over the last couple of decades. And this is, again, using these temporal model fitting and then relating it to field data on the practices to look at mapping. And this paper linked here shows a lot of validation of this data set. But mapping at very fine scales and at broad scales, the differences in practices that farmers use. So now we have, on the one hand, large data sets on the outcomes, things like crop productivity. And on the other hand, we have practices that the farmers are doing. We also have ancillary data on soils and weather, et cetera. And so we have a lot of observational data that we can start to actually look at not only where are these practices being performed, but what kind of effects do they actually have on outcomes that we care about. And so in this case, what we've done is look at using the causal forest approach, where we try to pull out from observational data the causal effect of, in this case, the practice of no-till on yields. And that ends up producing an estimate of the average impact, but also the heterogeneity of the impact. We don't expect any practice to have the same effect everywhere, and the models can actually begin to understand how those effects differ depending on where you are. So in this case, on the right shows our estimate of the spatial heterogeneity in that effect, but overall a positive yield effect of no-till adoption. And on the left here is shown a comparison between fields that have been in no-till for the entire record that we see versus fields that have recently gone into no-till. And this is in line with what our expectations were, which is that the benefits would accrue over time. So you wouldn't necessarily see them if you're looking right away. So hopefully that gives a sense of the types of supply chain monitoring that can be done. We're doing this in many countries, but I focus here on the US because that's where the data is most advanced, and given the time, I didn't want to try to do too much. So with that, I thank you for your time, and just list here a couple of ways to get in touch with me. Thank you.
Our next speaker is Justin Huntington. Dr. Huntington is a research professor at the Desert Research Institute in the Western United States and the Chief Science Officer for Climate Engine. His research focuses on remote sensing, evapotranspiration, irrigation, drought, and hydrologic modeling. He has built operational remote sensing data systems for a variety of organizations, including the U.S. Bureau of Reclamation, the U.S. Geological Survey, U.S. Bureau of Land Management, NASA, and the state of Nevada. Dr. Huntington is a member of the Landsat science team. Today, he will be presenting on the science behind drought monitoring and building of early warning systems. So over to you, Justin.
Well, thanks, Tyler, for that awesome introduction. Really appreciate it, and appreciate everybody's attention and time on listening to this Geo for Good talk on delivering place-based drought and water insights for early warning. So a little bit of background. Drought's really one of the biggest climate risks to agriculture, food production, and global supply chains, consumer packaged goods, equating to really a $60 billion at stake value here. And Earth observations can really help assess risk and early warning. However, dealing with these big data, and especially big data interoperability and being able to scale and going from research up to operations has really been a big challenge. And here are some recent news clips on how the recent droughts have really impacted supply chain with respect to everything from chip shortages in Taiwan to coffee production in Brazil to hydropower generation in California and other Western states. So achieving scale and going from archives to answers is really where our focus has been. And this whole concept of bringing the algorithms to the data and not the data to the algorithms like we used to do. And really, this is being more and more required to really efficiently go from data to decisions and really achieving scale. And also what we need from a user perspective and from water agencies and land managers are no-code solutions or minimal code solutions to really be able to pull out these insights. And so the challenge is really not the lack of data. We have plenty of that. The challenge is converting these data into actionable insights very easily. And so that's really where we have focused over the last many years, almost a decade now, really working to help deliver and develop geospatial data insights around sustainability, natural resource management, and early warning. We started back in 2014 with a Google Faculty Research Award grant from Google Earth Engine. We were one of the first, I would say, power users on Google Earth Engine, and our original focus was centered around drought. And really humbled and honored that we got the front cover of BAMS, the Bulletin of the American Meteorological Society, in 2017 around this idea of harnessing big climate data in the cloud. Since then, we've done successful tech transfer from the Desert Research Institute to our company, Climate Engine, when we started to get a lot of inquiries from the commercial sector around providing operational climate data insights and early warning. So Climate Engine brings together Earth Engine with a bunch of pre-configured API calls and a bunch of different data sets that are also not in Earth Engine. So Earth Engine has the world's largest archive of open Earth data, over 700 plus data sets. And Climate Engine also has a bunch of data sets that are custom data sets, over 100 custom data sets and over 90 pre-configured APIs. We also have a user interface for data processing and visualization. So we do all this data processing using Earth Engine and then serve out these data through APIs that then can be integrated into, for example, BigQuery or Esri or Carto and other applications. So really making it easy to go from large data sets to operations and visualization in an automated way. A good example of this is shown here, where we have a Google Earth Engine script in the code editor in JavaScript. We basically packaged up this JavaScript into a single line API call to make this long-term drought blend. And this is in the past, you would have to code all this up yourself in the Earth Engine API. And so NOAA has partnered with us to essentially help them operationalize these different data sets. And so this is shown here, where we've gone from research to operations, where we've developed this long-term drought blend and many other drought maps. And NOAA is now hitting the Climate Engine API every single night as a cron job to create the drought indicators in Earth Engine. Then we export those geotiffs to the to NOAA's Google bucket. And then they download those data and turn them into raster tiles and put their own color palette on there. And then they put them on these map cards on drought.gov under the current conditions tab. We also read custom data sets that NOAA puts in their bucket as cog-backed assets. So the Earth Engine's new cog-backed asset function is phenomenal, that we can read cogs in their bucket without actually having to move the data into Earth Engine. So we can operate on the cogs, produce the drought maps, and then write the results back out to their bucket. So here's the example illustration of our user interface. This is a trend in the US Drought Monitor map. It's this trend map I've never seen online. This is the first time I've really shown this off to the public, but basically this is a man Kindle trend test and send slope analysis, where you can see that in California, the drought is worsening over the last 21 years. We can download maps time series, and these are the statistics that are available, your kind of classical climate analysis statistics. So we have, like I said, the application as well as the API that you can make operational calls to. So this multi-source Earth observation data and FAIR data principles. So best practices that follow findable, accessible, interoperable, and reusable or FAIR data principles are really taking off. we're maximizing scientific insight discovery and improved natural resource management decision-making by having these fair data principles. And this is one of the beauties of Earth Engine, is that the data is interoperable, and we don't really have to worry about it. We don't have to worry about different projections, different cell sizes, mashing these different raster data sets together to make products. And an example here is combining all these different data sets shown here to produce other higher level products. And a good example of that is our consumptive water use project called OpenET, or Open Evapotranspiration, where we're essentially using 6 of very well-established land surface energy balance models to estimate ET, which is a key measure of agricultural water use and productivity, and also looking at changes in ET over time to assess water and production risks at the parcel level. So this is a really neat project that just got launched and is really making waves in the water resources community. Here's an example of evapotranspiration over time at the monthly time steps for 2 different areas in Nevada, where this top graph shown here, they are 100% reliant on surface water. And this area on the bottom, Mason Valley, they have supplemental groundwater. And so when we're starting to think about risk, agricultural productivity risk and drought risk, and which areas are at risk due to drought, we can easily find these places by being able to make maps like this and seeing drought cycles shown here in the colors that are not more tan colors versus valleys or areas that have nice, constant, and steady productivity shown on the bottom graph, and these green boxes that don't vary very much. So with respect to how we do this in Earth Engine, and really the power, this is kind of the architecture where we have all the different model inputs, lots of different data sets, like I said, with different resolutions. We do all the computation in Earth Engine with these different models, and then we post-process all these data, also using Earth Engine, doing our spatial reductions, spatial averaging to all the parcels, and then we serve all those data out through APIs and a user interface. So Earth Engine has really made this feasible to do, whereas in the past, we just haven't had the computational abilities and the storage requirements to do so. Another important aspect of all this is irrigation land type status, and really being able to quantify what lands are irrigated versus fallowed and also shorted. And so this was an Earth Engine project that recently got published, where for the entire Western US, we have irrigation status, which is also extremely useful for supply chain risk assessments and identifying shorted lands, what lands are consistently short, and what lands are consistently fallowed versus not. And so developing correlations with different drought indices and identifying risk for different areas and assets of interest at the parcel level, I think really has a lot of potential here. And then linking those results to supply chain questions around productivity risk, reliability, water availability, and then water right priorities, we can actually map who's got priority water rights from analyses like this, and then link it back to supply chain questions. So here are some global examples of, back to that coffee example that in Brazil that I recently highlighted, using multiple Earth observation data sets at different scales. Here's the recent drought in Brazil. Here's the percentile of total runoff from a hydrologic model showing the low percentiles in Brazil, and then seeing this through the lens of MODIS using NDVI percentiles, and then zooming in further to the regional scale, and then further zooming in using Landsat and making Landsat-based NDVI percentiles so we can get down to the plantation scale and then link it with assets or property owners to see what companies are really being impacted here. Here's just another example of the recent drought in Taiwan with respect to chip manufacturing and the Tichai Reservoir that supplies Micron in their production process. And you can see the reservoir levels in 2020 versus the big drought in 2021 that's ultimately affected supply chain to chips in Taiwan. And then thinking future and outlooks. This is the precipitation percent of average outlook for the next 28 days here at the end of October. And it's looking pretty good. So hopefully we will have a drought buster this year, at least for the next 28 days. Longer term, it's not looking this promising, but we'll see. In summary, climate risk to agriculture, global supply chains, and consumer packaged goods are really becoming more frequent and more extreme. This combining of place-based Earth observation data and forecast information really has been a challenge in the past due to the interoperability and big data requirements, but luckily today we have new technologies like Earth Engine, pre-configured functions, APIs, and no-code solutions like Climate Engine to really support that operational production to inform Earth insights and ultimately supply chain and many others. Thank you.
Hi, everyone. My name's Tyler, and I'd like to welcome you to the live Q&A portion of this session. I'm here with the scientists that you just heard from, Zoltan, David, and Justin, and we're here to answer your questions. So for those of you who have been asking questions during the presentation, thank you. Hope to get to them. And if you haven't, it's not too late. You can still submit your questions right now below the video, and we'll try to get them answered as best we can. I'm especially interested in questions that are relevant to each of the presenters' work, hoping that we can explore common themes that are applicable to anyone who's doing scientific research with an eye towards how getting their research into application. So, okay, let's ask our first question of the panelists. So the first thing I'm going to ask about is sort of the path of transition from research to actual use. Each of you presented on techniques that can be used to estimate information relevant to the food supply chain, although they're also relevant to other supply chains as well. Zoltan described techniques for global mapping of a particular crop, oil palm. David described techniques for estimating yield and the effect of conservation practices. And Justin described monitoring threats and impacts to agricultural production due to drought. So for each of you, could you describe any barriers or successes that you've had in getting your research into the hands of the organizations that are working on these supply chain issues? So let's start with you, Zoltan.
Thanks, Tyler. Hello, everyone. So for the oil palm map, as I showed, we use deep learning, which in many cases is particularly useful and can deliver very accurate results. So such algorithm, when features such as textures are distinct regardless of the data source, radar or optical, can perform very well. Because I would generally attempt to discriminate between a certain crop versus everything else, or basically we could just look at it as a binary classification rather than trying to separate many types of land uses. In our case, such methods work perfectly well. And once we had the oil palm areas, we could focus on the separation of smallholder versus industrial plantations using features which are recognized between them.
So the successes relative to the technique that was being used, innovative techniques. David, I'll pass the same question over to you. Could you describe any of the barriers, successes that you've had in getting your research results into the hands of organizations?
Yeah, thank you, Tyler. I guess there's a couple levels that we interact with policymakers and users. I think one, and the kind of things I presented are just basic questions around what practices should be encouraged in different parts of the country. So whether I talked about no-till or crop rotations or cover crops, things like that, there's just not so much a demand for the data itself, but just a demand for evidence on what does or doesn't work. But at another level, there are supply chain modelers out there that understand sort of where is the catchment of producers that feed into certain companies' supply chains, and this kind of data could be used in that way as well, though we haven't really pursued that yet.
Thanks. And Justin, could you describe it in terms of your drought-related work that you presented on?
Yeah, sure. Thanks, Tyler. Going from R to O or research operations has been a bit challenging, but I feel like we're finally there. And one of the big things that helped us was basically making APIs, custom APIs for certain products that we were developing using Earth Engine, and essentially collapsing all that code down to simple API calls, and then running using our own custom APIs then to operationally update and create the data using Cloud Run and Cloud Functions. And then giving the agencies that are using this information example API calls so that they can then use those API requests operationally on their end. Also, it's much more than just having them download the data. Oftentimes, it's about providing the insights and the descriptions of what these data mean, the storytelling behind it, to then form summaries and reports. And oftentimes, those reports end up going into litigation and courtrooms. And so, having the science behind that information in the form of a report is really important, and that's really helped go from R to O.
Well, thanks. I'm going to then go to one of the questions that was asked by the audience during the presentations, and this one is for David, and it's from Jyoti S. Hope I pronounced that correctly. Dr. Lobell, thanks for your presentation. What are the challenges to reducing the latency of your no-tillage dataset models? What would be approaches to infer these practices on the same crop year, for instance?
Yeah, latency is certainly an issue if you're going to operations. It's less of an issue for what I talked about of just doing the research and getting the insights. In that case of like no-till, it really depends on when the key signatures are appearing in the season. And luckily in the case of no-till, it's very much before the season has even started, often in the fall before you would see the tillage event happen or not happen. So that's a fairly easy one. But there is also a lot of work ongoing in doing very early season mapping, for example, of which crops are being grown where, and other aspects of, like, say, cover cropping. So there is a lot of, I think, emphasis now on trying to train models to not only do a good job overall, but to do a good job as early in the season as possible.
Yeah, that's timing of the prediction can be very important for certain use cases. The next question we have is for Zolti, and this is from Jacob A. It says, thank you very much for the great presentation. In your paper, it states that training and validation data was digitized from the Google Earth Engine base map imagery. Do you feel this data is sufficient to replace ground truth data, even though it does not have date timestamps? Additionally, why only use band 4 of Sentinel-2 imagery rather than all the bands, or only the polarizations VV and VH, not the ratio or difference as well of Sentinel-1? I'll leave it there. There's a little bit of a follow-on, but I'll ask that or answer that first.
I see quite many interesting questions in there. Maybe let's just go with the first part first, the ground data collection. So yeah, in fact, Jacob, we collected the data through Google Earth Engine base maps, and well, for several reasons, especially now with all what is happening in the world, very hard to go on the ground. Firstly, secondly, not even very hard; it's very expensive to go on the ground. So using good quality base map imagery, I think it's partially the way to go. Now, you mentioned the timestamps for oil palm in particularly. It was not really an issue since they are planted and they are there for 20-25 years. So I think in the case of it, you just have to look at which crop you are working with. For a maize, probably a timestamp imagery is very important, but for oil palm, again, it wasn't a major issue. The other part was you asking about band 4. It's just sake of simplicity. Band 4 from Sentinel-2 was just good enough what we needed for. So we didn't need to use any other optical bands to detect the road network, which we actually, the Sentinel-2 data was only used for to find the oil palms or discriminate the oil palms from other type of vegetation. We actually used Sentinel-1. So we didn't want to, even though we worked in a cloud environment, we didn't have to use all the data what we needed for the purpose we were using it for. I let the others talk too.
Okay. Does anybody else want to add to that?
Well, I guess I can add. I mean, the question was specific to that project, but we also find Sentinel-1 very useful for certain things and not for others. And especially when we're looking at mapping where, say, tillage was, it was fairly useful, but it's really useful when we're trying in tropical areas where the cloud cover is dense, trying to do the type of crop type mapping that I described for the U.S. In the U.S., you can get by without radar, but it really does seem to help quite a bit in lots of cases. And we use the ratios as well as the raw bands, but depending on the model you're using, it can often figure out that the ratios are useful by itself.
Yeah.
Thanks. Let's now go to a question for Justin. This is from one of my collaborators behind the scenes. It says, it's interesting to turn some lines of code into one line of code, but how about no lines of codes? In your experience, how do policy and or decision makers consume results from Climate Engine? Do they want to code?
Yeah, that's a great question. And that's one of the main reasons why we developed the user interface of Climate Engine at app.climateengine.com. We wanted to provide a no-code solution for Earth Engine so that you could, for example, pick Landsat, compute NDVI, draw a polygon, and get the time series of NDVI for a season average, or get the time series at the native temporal resolution for not just one polygon, but maybe thousands. By uploading a feature collection ID. So yeah, they don't want to code. But in terms of, for example, the thousands of polygons, we steer them towards our API, in which they can construct an API query request using, for example, Swagger that builds the query string for them, and then they can just submit it at the browser level or as a curl command. So in my experience, you're right. They don't want to code. They want a no-code solution for Earth Engine.
All right. I'm going to go back to another question from the audience. This is for David from Santiago V. Hi, David. Thanks for your interesting presentation. Have you tried the harmonic regression approach over fields sown twice a year?
Yes, yeah, actually we've done that. In the US, there's obviously only a few places that tend to double crop, but we've done a lot of work, for example, in South Asia, where 2 crops a year is the norm. And it does work very well in that situation. So, one of the challenges when you're building a machine learning model is to make sure the labels are for the seasons that you're looking at. And sometimes you have to be careful in a double cropped environment that you are that you know what you're trying to predict. But beyond that, yes, it is generally quite useful. And that's particularly important in these tropical areas.
Great. Now I'm going to go to a question for Zolti from Cheryl Q. Great presentation. You mentioned your next tree map will be coconut. Are there other plantation types you and your group will produce?
Thanks for the question. Yeah, we are always looking into what is important for policymakers or for the supply chain, in fact. And yes, we are already working on coconut. And in general, vegetable oils or plants which we use to produce vegetable oils are in our view. So This could be soybean, which you already have, of course, some, if not necessarily global, but at least regional level maps, but some other vegetable oil plants which are not really looked at, but some are very hard to map based on satellite data. So, but we are thinking along these lines.
All right, we're down to just a few minutes left, so let me ask potentially the final question and try to limit yourself to under a minute in responding. What are the main challenges in your research area, or in other words, what directions do you tend to take this next? So let's start with Justin on that one.
Oh, geez. More, bigger, better. I feel like one of the main challenges we have right now is getting more data into Earth Engine so we can use it in a more operational way. For example, we're ingesting the harmonized Landsat Sentinel product on our own right now for certain areas. It's a big lift for us, as well as daily average data from Era 5 land. And going back for the whole historical time series and computing drought indices and looking at trends in drought indices using Era 5 land at daily time steps. And so, just bringing more data into Earth Engine, either through our own work or working with Earth Engine directly to get some of these data sets added. And also bringing data from Earth Engine, for example, into BigQuery and doing feature-based analyses rather than raster-based analyses.
Thanks for that. Same question to you, David. What's the future look like for your research for you in a group? I realize you just presented mainly on work in the United States, but...
Right. Yeah, I mean, I think the challenge in general when you go around the world is training data. Now that Earth Engine and other platforms have done such a good job of getting all of the imagery data in one place. And so I think there's a lot of exciting stuff going on in terms of different ways of crowdsourcing labels and also kind of fusing different data sources. We're now very excited about the JEDI data being ingested, the spaceborne LiDAR data, which can itself be a useful predictor, but it can actually be used to train other models. And so, I think there's a lot of exciting development on the rapid training to get more localized models, which have higher accuracy. And then I think what Justin mentioned is certainly a challenge of trying to get beyond like pixel-based operations and getting more connectivity between Earth Engine and the deep modeling capabilities, which I know has been on the radar for a while.
Well, thanks for that. And unfortunately, Zoltan, I'm going to have to skip you on that last question so we can wrap up this session. I want to thank everybody for joining us today. Please stay tuned for the Sustainable Supply Chain Sourcing session next, and have a great summit, everyone.
Thank you all. Thanks.